Hello and welcome to the sample lesson from physics, Edexcel Physics IGCSE. This is chapter 19, solids, liquids and gases. It all started in England in the 16th century when a science teacher called John Dalton proposed the theory of the particle theory of matter, at which that all matter is made up of tiny particles, which of course we now call them atoms. The word atoms comes from the Greek word atomos, which means cannot be cut. The theory as well states that the particles of the same substance are identical, which means atoms of the same substance or molecules of the same substance are identical. These particles, atoms or molecules, are in constant motion, which means they are never still, even in solid form. Temperature or the surrounding temperature affect the speed at which these particles are moving. So higher temperatures corresponds to higher kinetic energy or higher speeds, while lower temperatures is connected to lower speeds. Of course, as we can see in here, in this figure, we have a mixture of molecules, and of course, this is a pure substance. Here, of course, in this container, we have only oxygen, while in this container, there's water vapor, oxygen, and other gases, which of course, the air that we breathe. One of the main scientists that worked on the motion of particles was Robert Brown. And he discovered what we today we call Brownian motion, which is the random motion of particles in space. Take an example, for example, smoke. When you see smoke taking different directions while it's moving through the air, that's because of Brownian motion. And the reason that these particles, the smoke particles, are taking different directions is practically the collisions with other particles in the air, like oxygen, carbon dioxide, and other gases. Now, for states of matter, we all of course know that there are three main states of matter, which are solid, liquid, and gas. And of course, we are gonna look at the properties for each. For example, solids. The properties of solids that they have a fixed shape with tightly packed particles. In other words, the particles in a solid are very close together that they can't move apart. They practically only vibrate in place. The packing of the particles results in solid having high densities and toughness and strength. High toughness and high strength, meaning you can't break or move it easily. These particles vibrate in place. The more energy supplied, in other words, as I described before, the higher the temperature is, the more energy supplied, and so the vibrations will be faster. Now, the properties of liquids. Liquids don't have a fixed shape. In other words, they fill the container they are placed in, whether of course it was a glass or a jug or any type of container. Their particles, of course, are close together. The particles of a liquid are close together, but they are not as close as in solids, and that's why they have, this flowing property. These particles move freely and randomly, which means they slide on top of each other, but still they are connected with some forces that gets these particles together. That's why, for example, when you spill water, you see that the water moves in one direction because the particles are attracting each other. Now, the properties of gases. First of all, gases don't have a fixed shape. Of course, we all know that. And they fill, and the particles spread out to fill the entire container. So we don't put gases in a cup because this cup is part of the room, and so the gas in the cup is gonna fill the entire room. Now, the spaces between the particles in a gas are very far apart compared to liquids and solids, and because of course the forces that are holding them together are weaker. Particles of a gas, of course, move slowly and randomly and in all directions. There is no certain direction because, of course, it's random. The motion is random. The gases can be compressed easily to make the spaces between the particles smaller. And that's, of course, why we sometimes hear that they take oxygen and they make it into oxygen as a gas and they make it into liquid oxygen. That's, of course, by compressing and cooling the gas into becoming a liquid, eliminating the great distances or spaces between these particles. Now, to sum up, the properties of solids, liquids, and gases, which has a definite shape, only solids, can be compressed easily, only gases. Of course, we can compress liquids and solids, but it's not as easy as compressing a gas. The relative density for the three states, the solids and liquids have high densities, while gases have low densities, of course, because of the great distances between the particles. Which of these states can flow? Solids obviously cannot flow because, they have a fixed shape. Liquids, on the other hand, and gases can flow. They can move from one part of space into another to fill it. Now, expands to fill the available space, the entire available space. Only gases can do that. Liquids is gonna fill as much as it can, but it doesn't expand to fill the entire room, for example, while gases can. Now, regarding the shape, as you can see, solids have tightly packed particles, and of course, everything is uniform. While in liquids, they move in different directions and they have random motion, but still, relatively, the particles are close together. While in gases, they move faster, the particles move faster, and the distances between the particles are pretty great. Now, measuring thermal energy, or in other words, temperature. Temperature, of course, is thermal energy is another word for temperature. When we say thermal energy, we're talking about energy as heat, giving or taking heat from something. Temperature is a measure of the kinetic energy of the particles in a sample. In other words, the higher the temperature of a sample, whatever that sample was, a piece of iron, some water that you put on the stove to boil, or even the air surrounding you, have a certain temperature. And the higher the temperature is, the more kinetic energy the particles of that sample have. They move faster. The faster they move, the higher the temperature. If we supply more thermal energy into the sample, this will increase the kinetic energies of the individual particles in the sample in a way that it will make the particles move faster and faster. So when you put some water on the stove to boil, you notice that after some time, all of the water has evaporated after boiling. Why is that? It's because the more energy, in other words, more fire, more heat I'm giving to the water, the more energy is being absorbed by the individual particles, which makes them leave and escape out of the liquid and into the air as gas. Now, different substances need different amounts of energy to increase the temperature. So heating water is not the same as heating iron or heating paper, for example. Each substance needs different amounts of energy to get heated or to increase its temperature. For example, if we look at the structure of molecules in a water substance in all three states. Of course, the most common form that we're familiar with water is liquid water, as you can see that the particles are tightly packed together and they have different orientations. In other words, they have not a specific direction that they are oriented in. Now, if I supply a lot of energy, more thermal energy to this sample of liquid water, these particles are going to start to move faster away from each other and the distances will start to increase, turning the liquid water into gas. Now, on the other hand, or conversely, if I take away energy or thermal energy from the liquid, from the liquid state, it will turn into ice, or it will turn into a solid. Now, the specific heat capacity, or SHC. The specific heat capacity is a measure of how much energy a certain substance needs to increase 1 kilogram of it by 1 degree Celsius. So, for example, water needs a certain amount of energy, and of course from previous classes you do know that we measure energy in joules. So it needs a certain amount of joules to increase 1 kilogram of water by 1 degree Celsius. We use, of course, the following equation for measuring the difference in thermal energy of a substance, whether, of course, you're supplying it with thermal energy, in other words, increasing its temperature, or you're taking away thermal energy from it, or you're making it colder. The equation is delta Q. Of course, we all know that delta is the symbol for difference in, Q is the thermal energy, equals to M, the mass, multiplied by C, the specific heat capacity, which is a constant number for each substance. That number does not change. And delta theta. Theta, of course, is the symbol for temperature. Delta is the difference in, and the difference in means the final temperature minus the initial temperature. Let's take one example of how we can solve a question regarding the specific heat capacity. If you fill a kettle with 300 grams of water at an initial temperature of 15 Celsius, how much energy is needed to make the water heat up to boiling? The specific heat capacity, or SHC, of water is 4,200 joules per kilogram per Celsius. Now, I'll say it again, that the specific heat capacity of a substance is a constant number that does not change. So for water, it's 4,200 joules per kilogram per Celsius, and it remains that way. Now, for the solution, first of all, we have 300 grams of water, but I want it in kilogram. Remember that the specific heat capacity has the unit kilogram in it, and so I need to convert grams into kilograms, and to do that, we're going to have to divide by 1,000 to get 0.3 kilograms. The specific heat capacity is 4,200 joules per kilogram per Celsius. Now, the initial temperature is 15 Celsius, but the final temperature is 100 Celsius. Why? Because it says that the initial temperature is 15 Celsius. How much energy is needed to make the water heat up to boiling? So I'm trying to boil the water. And of course, for water, boiling means 100 Celsius. Which means delta theta, or the difference in temperature, would be the final temperature minus the initial temperature, equals to 100 minus 15 equals to 85 Celsius. Now I do have all my data, and I need to implement it in the equation to find the difference in thermal energy. How much energy do I have to supply this water to boil it? So delta Q is equal to M times C times delta theta, which means 0.3 multiplied by 4,200 multiplied by 85, which means that it's 107,100 joules, or just 107.1 kilojoules of energy. So 107.1 kilojoules of energy is required to increase the temperature of 300 grams of water from 15 Celsius and into boiling. Let's look at another example, example number 2. In an experiment to measure the specific heat capacity of aluminum, a cylinder of mass 0.5 kilograms or half a kilogram, of course here we don't have to convert because it's already in kilograms, initially at 20 Celsius was supplied with 16,500 joules of energy. Now we do know how much energy it was supplied. At the end of the heating, the temperature had risen to 50 Celsius. So it was 20 and it had risen to 50, meaning 50 is the final temperature, while 20 is the initial temperature. Calculate the specific heat capacity of aluminum. So here we need to find C. We do have Q or delta Q. We do have the final and initial temperatures, which means we can find delta theta. We do have the mass as well. We only have C, that is unknown. The solution: if M was 0.5 kilograms, delta Q was 16,500 joules, delta theta is the final temperature minus the initial temperature, equals to 50 minus 20, equals to 30 Celsius. By rearranging the equation, delta Q equals to M times C times delta theta, for C, solving for C, we'll get the equation C equals to delta Q divided by M times delta theta. So, C would equal to 16,500 divided by 0.5 multiplied by 30, which would equal to 1,100 joules per kilogram per Celsius. Which means that it needs to increase the temperature of aluminum by 30 degrees Celsius, we have to supply it with 1,100 joules per kilogram per Celsius, which is less than water. We did see in the previous example that water had needed 4,200 joules per kilogram per Celsius to increase its temperature by 1 Celsius per kilogram. And this tells us how different substances have different needs to increase or decrease their temperature. Metals are good conductors of heat, and that's why they require less energy to heat them up, while water is a poor conductor of heat, and that's why it needs less energy. More energy. Example number 3, page 185. To determine the specific heat capacity of water, 1 liter of water at a starting temperature of 20 Celsius is poured into an electric kettle with a power of 2.4 kilowatts. The water in the kettle just reaches boiling point after 2.5 minutes. Use this information to calculate the specific heat capacity of water. Do you think your answer will be too big or too small? And give reasons for that. Now, this example is a little bit tricky because we do have the power of the kettle and we have the time at which it took the water to increase from 20 to 100 to boiling. The mass is 1 kilogram because 1 liter of water is equal to 1 kilogram of water. The power is 2.4 kilowatts, which means it's kilowatts. I want it in watts, so I'll multiply by 1,000, which means that the power would be 2,400 watts. The time was 2.5 minutes. In seconds, that's 150 seconds. And the difference in temperature, or delta theta, is equal to final temperature minus the initial temperature, which is 100 minus 20 equals to 80 Celsius. Now, this is a bit tricky because we're going to have to use the power to get the amount of energy supplied to the kettle. Now, the power is equal to the energy divided by time, and to find the energy, I'm going to have to rearrange that to find the energy, which means energy is going to be equal to the power multiplied by the time, or 2,400 watts multiplied by 150 seconds, equals to 360,000 joules. And of course, E is delta Q because both of them are energy. By rearranging the equation, delta Q equals to M times C times delta theta for C, we find that C, or the specific heat capacity, is equal to delta Q, or just E, divided by the mass multiplied by delta theta. And by substituting what we have, the specific heat capacity is equal to 360,000 divided by 1 for kilogram, multiplied by 80 Celsius. And so the specific heat capacity is 4,500 joules per kilogram per Celsius. Now, another part of the question says, do you think that your answer will be too big or too small? And give reasons. Of course, looking at this answer, which is 4,500 joules per kilogram per Celsius, is more than what we expect, because we do know that the specific capacity of water is 4,200 joules per kilogram per Celsius. Now, there's an increase of 300 joules per kilogram per Celsius. Where did that come from? The fact that some of the energy supplied to the kettle went into heating the kettle itself, and the kettle of course will be made out of metal and plastic, and of course metal and plastic has their own way of absorbing thermal energy. Okay, thank you for listening to this for this sample lesson from the IGCSE, and I wish you good luck.